Our world faces a resource crisis. Humanity's relentless demand for rare earth elements for advanced electronics, clean-burning nuclear fuels, and next-generation batteries is pushing our home planet to its limit. And that is before we even start to consider the raw materials needed to build out the sustainable energy infrastructure required to power our growing global population. Terrestrial mining causes environmental damage and geopolitical tensions. So could the answer to this problem lie above us amongst the stars? Could space mining be humanity's ticket to an abundant future, or will it end up being another wild goose chase like the 19th century gold rushes? And assuming that it doesn't result in a new battleground for world powers, could asteroid mining actually work? And if so, what might the benefits be? Before we set off into the asteroid belt, or maybe the moon, let's define exactly what we mean by space mining. This isn't some futuristic concept. We have been mining the moon since the 1960s, when the Apollo astronauts brought back hundreds of kilos of lunar regolith or surface material. But that was just a tiny amount compared to the wealth of resources present on the moon and other nearby celestial bodies. So far, most asteroids and the moon have been targeted for mining are those located relatively close to Earth within the asteroid belt between Mars and Jupiter, which means they require only moderate amounts of fuel for a spacecraft to reach them. The most popular target is 100 miles wide asteroid Psyche, which is composed mostly of iron and nickel. But there are plenty more targets to choose from. Some recent surveys suggest there could be as many as 1 million asteroids measuring over 1 kilometer in diameter, within reach of current generation rockets. Earth's moon is also an attractive option as it hosts large reserves of water ice at its poles, which can be split into hydrogen and oxygen, both of which are crucial for rocket fuel and life support. Not to mention the vast quantity of silicon dioxide, aluminum oxide and titanium oxide found in lunar regolith, all of which are important ingredients for glass making and steel production. But how exactly might we extract these resources from hostile environments with no breathable atmosphere, extreme temperatures, and lethal levels of radiation? Robots would likely be our first line of defense in space mining operations. Autonomous drills and diggers would be employed to bore into the surfaces of asteroids and the moon, gathering up vast quantities of regolith and feeding it into waiting trucks and trains. This material would then be loaded onto reusable shuttles, ferried back to Earth, where it would be processed to extract useful minerals. Large-scale space mining operations would almost certainly employ orbiting facilities. The most feasible designs for these platforms would likely be made from inflated modules, similar to the Bigelow Expandable Activity module currently in use aboard the International Space Station. These structures could accommodate large crews of workers, provide ample space for resource processing equipment, and allow for the manufacture of large objects in space, such as components for solar power stations or even the hulls of deep space vehicles. To keep the human element safe, asteroid mining platforms would have to be designed to withstand micrometeorites, deadly bits of space debris traveling at high speeds. They would also have to compensate for the effects of microgravity on the human body. For these reasons, many space mining companies are designing their platforms to rotate, creating artificial gravity for their inhabitants. This could be done by spinning the station or by rotating sections of the station independently. Artificial gravity could help to maintain the physical and mental health of miners during long-term space missions. The key to cost-effective space mining will be automation. Robots and remote control technology will be used extensively to minimize the need for human intervention and reduce the cost of operations. It is likely that we will see the rise of self-replicating robots that can create copies of themselves using locally sourced materials. These machines could rapidly deploy across large areas, greatly speeding up the extraction process. 3D printing in space is also becoming increasingly viable thanks to innovations such as the use of metal and ceramic-based filaments which have higher melting points than materials used in terrestrial 3D printing. Using local materials, whether that be lunar, regolith or asteroid rock, in situ resource utilization or ISRU. 3D printers in space could fabricate tools, replacement parts, and even entire structures without the need to ship materials from Earth. Propulsion is another area of intense research and development related to space mining. Breakthroughs in this field will be essential to reduce travel time to and from mining locations and make the logistical operation of shuttling resources back to Earth more cost-effective. One promising new technology is the solar sail, a large, thin film of material that can be deployed behind a spacecraft to harness the pressure of sunlight and push it along. This could allow for faster and more efficient travel between Earth and the asteroid belt. And once we're there, how exactly could asteroid mining power our future here on Earth? Let's look at a few possibilities. Currently, one of the biggest obstacles to developing renewable energy infrastructure is the cost of manufacturing solar panels and wind turbines. These structures require large amounts of rare earth elements, materials that are in limited supply on Earth and often have to be mined under difficult conditions. But many asteroids and the Moon are rich in these elements, which are called platinum group metals. Platinum, palladium, rhodium, iridium, ruthenium and osmium. These metals are highly valued on Earth for their use in catalytic converters, electronics and jewelry. Platinum group metals are also extremely useful in space because of their resistance to corrosion and high melting point. They could be used to construct the mirror-like surfaces of large orbital solar power stations, beaming microwave or laser energy down to Earth. Such stations could be built from asteroid or lunar materials mined in situ and assembled on site using 3D printing techniques. Or they could be constructed using ISRU and a large fleet of robotic assemblers. These giant mirrors would collect energy from the sun and direct it towards large rectennas on the ground. Rectifiers would convert the incoming electromagnetic radiation into electricity and distribute it to the grid. According to NASA, a single 1,000 megawatt optical wavelength solar power station operating at an efficiency of 20% could meet the total electricity requirements of approximately 20 million people. The potential of such a system for providing clean and abundant energy to large populations in densely populated regions makes the prospect of orbital solar power particularly appealing. Another possibility is using materials harvested from space to build out a new infrastructure for deep space travel. In fact, NASA has already given this some thought. Their current plans call for a large fleet of reusable cargo, ships to transport people and resources to and from the Moon and Mars. These vessels would be partially manufactured on the Moon using 3D printing techniques and local resources. This would dramatically cut down on the amount of material that needs to be transported from Earth and make it much easier to establish a permanent human presence on the Moon and Mars with more advanced technologies. We may even be able to mine asteroids for materials that can be used to build giant generation ships capable of taking people further into deep space. But what about the money? Who's going to pay for all of this space mining infrastructure? Who owns the resources once they're extracted from asteroids and the moon? The legal and economic implications of mining in space are still largely unknown. Currently, there are no international agreements governing the ownership of resources extracted from celestial bodies. However, there are several international treaties related to outer space that could provide some guidance. For example, the Outer Space Treaty of 1967 establishes that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. However, this treaty does not specifically address the extraction and use of space resources. Some countries have taken unilateral approaches to this issue. For example, the U.S. passed the U.S. Commercial Space Launch Competitiveness Act of 2015, which allows U.S. citizens to own and sell resources they extract from celestial bodies. Other countries, including Canada, have expressed support for this approach, while others, including China, Russia, and the European Union, have not. It's clear that there is a lot of money to be made in asteroid mining. Estimates suggest that just the platinum group metals present in the near-Earth asteroid Psyche alone could be worth over $10,000 quadrillion. That's enough to make a few billionaires out of everyone on the planet. This rush for interplanetary riches could spark a new space race. Unless international cooperation is established to govern the use of resources and prevent conflicts in space. Another concern is that space mining could exacerbate existing inequalities between nations. Access to space resources could be limited to a few wealthy countries, potentially leading to new geopolitical tensions. On the plus side, space mining could create millions of new jobs and generate trillions of dollars in revenue. It could also help to diversify our resource base away from finite supplies on Earth, which are often subject to political instability and environmental concerns. Space mining could also play a vital role in our long-term survival as a species. Asteroids and the Moon are remnants from the early days of the solar system. They provide a window into the past and can tell us a great deal about the conditions that led to the formation of Earth and the origins of life itself. By studying these objects, we can learn more about our place in the universe and the challenges that lie ahead. As we continue to explore and expand our civilization beyond our home planet. In the long term, space mining could help us to establish a true multiplanetary civilization and ensure the survival of our species in the event of a disaster on Earth. In conclusion, asteroid mining holds tremendous promise for humanity's future. By harnessing the resources of space, we can alleviate pressure on Earth's finite resources, drive down costs, and create new industries and job opportunities. While there are significant technical and logistical challenges to overcome, the potential benefits are too great to ignore. As we continue to explore and understand our universe, we must also strive to ensure that the benefits of space mining are shared by all nations and that the risks are mitigated through international cooperation. Only then can we ensure that this new frontier is one that benefits all of humanity and helps us to build a brighter future among the stars.